So, Pana, did you attend my webinar yesterday?
Sometime question. It was
Okay. Yeah, we have Suresh joining. Hi, Suresh.
Hi, how are you, Prashant?
Good, good. Okay. I think we can get started.
should have made you the host.
Okay. So Tim, okay, do you want to start? Okay, recording is also good. Tim, thank you very much for your time and coming and sharing your insights on the graph databases. Looking forward for this. And most of you I see that are part of DBP. They know Tim well. Tim is an expert in data integration, especially, and of course he has worked in other areas in IT as well, including SAP, Ariba, and all those places. So Tim, over to you. So the floor is all yours. People might still be joining, but we'll get started.
Thank you, Prashant. I'm happy to be here to share a little bit about the research we're doing at the University of Calgary. I'm a PhD candidate there, and so I want to share a little bit what we're doing in regards to data quality and data integration and these kind of things because it's very dear to my heart. So I will share my screen here and walk you through the presentation of for today. The talk is basically the topic of the title is semantic transformation using acyclic graphs. It sounds very complicated, but once I walk you through it, you will probably get the gist of it. What we're trying to do in our research project here at UFC in the Department of Engineering at UFC. So the basic concept is such that we are talking about integration. Integration is not only application to application and integration. So from a source app to a target app or a consumer app, we have also data capturing capabilities. And then what we do is we send that data. We can also send data to a pipeline and to data analytics capabilities so that we use that data to drive dashboards, decision making, and so forth. What happens here is this is where we are. That's kind of the focus of the area of the talk. Is this transformation piece that happens when data is in movement and throughout the organization, also with the business partners. I maybe want to do this full screen so that everybody can see better. One sec here. I will change this to from the current slide. So when we talk about integration, and that's how I kind of explain it, integration is basically made up of 2 or 3 fundamental components. There's a transportation piece, and that is where we send messages from point A to point B. And that's the transportation component is primarily focused on routing, figuring out, and we'll differentiate there between contextual and message-based routing. Then with the second part is that we talk about transformation. That's actually the translation of the data. And here we divide it up into syntactical and semantical transformation. So the syntactical piece is when we take the structure of an incoming message, be it XML or CSV or whatever you have, JSON, and we take that and we transform that into another format, structurally into another format that the receiving or target application can consume and process. Semantical transformation is an area that is quite new. There's a lot of research being done in that space, and that's actually where we are focusing our efforts on. And that is where we try to maintain meaning of the data from the source system to the target system. And here we're talking about, for example, when we get a status code coming in or an invoice code coming in, and we have to maintain that code in the other application, and we have to pass on that meaning, but the target or consuming application really doesn't understand what the source application is talking about. And then the third component when we talk integration is the orchestration, right? So that is basically pulling the transportation and transformation layers together and putting some kind of management capability to it so that we consider sequencing and how things flow. It's more the process design of the whole integration scenario that we are talking about. So when we look at
Tim, on the orchestration, so
Mhm.
if you take an example like a transportation, it's from, let's say you are moving the invoice messages from system A to system B, and transformation is about, in the invoice there is a volume in barrels, and you want to transform it into meter cube. That would be part of transformation. So in
correct.
orchestration, what would be that kind of an example if you take what I just mentioned now? How does orchestration?
For example, that you want to make sure that customers go in first before you have orders coming in, right?
Oh, okay, okay.
So
Right.
that is basically you basically manage the dependencies between different integration scenarios and then linking them together. And there are tools out there that they are very similar to process design tools that help
Got it,
you
got it.
in the information,
Okay, that
right?
makes sense. Okay,
Yeah.
okay, okay.
So when we look at transactions coming through, and this is just a scenario here, we can monitor the messages coming in, and we can see the volume of messages that are flowing through the system at any given point in time. And this is a real-time scenario where I build a dashboard for. Different color combination basically shows the different types of transactions that we are getting that are coming through from any kind of source system that goes through to some kind of a target system. And you can see by day here how it fluctuates, and you can see on the weekend, you can actually clearly see the weekends here coming through, that there's no traffic coming through these messages. And those messages that are coming in or into the integration layer have to be then transformed semantical and syntactical, and in order to be sent out to the respective target system or consuming application. As I mentioned already, that we differentiate message transformation or message mapping in syntactical and semantic transformation. And where our research is focused on is on the semantic form, and that basically we want to maintain the meaning and trying to figure out how do we go and maintain that meaning as we move this data through the application. We are not interested in a syntactical transformation because there's a lot of tools out there. The vendors, the software vendors have TIPCO and so forth. They have done their job on that, and it's very, very stable and mature environment. But in the semantic area, there's still a lot of work that has been done, and that is where our research is focusing on. So the current problems that we are facing with semantical transformation is that we are dealing with structures that are just too rigid, right? So we basically have a value coming in and a value going out. And most of the time, the way we solve this problem today is we're creating cross-reference tables, right? That's the simplest form. We're going in and we're saying, okay, value A is value B. It's like a key value pair that we're, and then the integration layer goes and it does a lookup into these cross-referencing tables and then tries to retrieve that the appropriate data, right? But these cross-referencing tables are very, very rigid. They don't allow very quickly to adjust to business requirements that are changing and so on. And also somebody needs to maintain it. Entropy is a big issue. The quality degrades over time. And then of course, somebody has to maintain it. The question is, who is going to maintain it? You just can't drop this all into an MDM system because most of the data is user data. The business data, the business users will understand that. And then, of course, if you don't have these tables maintained properly, then you have errors. The integration will fail, or transactions will fail as they come through the system, and you have to have error messages, and you have to resolve that. So the question fundamentally for us, or when I started this research, is saying, is there a better way to do this, right? So is there a way that we can do these cross-reference schemas so that we can maintain these schemas autonomously, right? And is there a way that we can inject AI into this artificial intelligence in these cross-reference tables so that the system actually will figure it out what the cross-referencing should be when there is a failure in these, when a failure should occur and when it can't find a value that hasn't been maintained. So the conceptual idea was in 2020 that I had, actually a little earlier into 2019. And I drew up a kind of a concept diagram, and I said, okay, here's a source application, and then we have the standard middleware that is out. Every other company has that, whatever product they're using. And then we have a target application. And I said, well, let's keep this syntactical transformation inside the middleware. They know that best. But why don't we build a service offering around this whole semantical transformation, come up with a new approach of how to deal with that. And that's kind of where I was going with this, right? So we have some kind of a database here, and then we have some kind of a way of machine learning capability that goes and analyzes this data as it comes through. And at the time, I really didn't have any clue of how we're going to do all of this and how it actually going to work. And as over time, as we did some work on it and looked at different options in order to build this basically this solution for this semantic transformation, things matured over time. One thing I noticed right away was when we look at cross-referencing, we find that it's almost a basic database by itself. There's a lot of referential integrity that happens, and this is kind of an example where we have an application tied to material and material to do some kind of material cross-reference. That is basically where we map the receiving code to the target code. And then we have some location codes that are tied in there. So it's a very, very structured database with a lot of referential integrity. And so as you go through here, it's not just looking up a key value pair, it is actually finding things inside of this schema in order to find the right value for your requirements that you're doing right now when you do a semantic transformation. So I looked at this and I said, okay, well, this is not going to work. A normal standard SQL database is definitely not the way to go on this one. So I started looking at graph databases and started to build, looked at RDFs and so on. It gets quite technical right now. But I basically came up with a graph database that is really, really suitable for this problem. And it took me a while to work through the data, but I basically took the standard traditional format and converted that into a graph database. And what the graph database, the exciting part about this is that it is so agile, we can actually do anything we want with this thing on the fly. And so every node, you see the nodes here on this graph, and this is actually a screen print out of the tool, the database that I'm using. You can see here the path that is going. Every node can be an entry point, and I can go from any node here and traverse through this whole graph topology, and I can find things as I traverse through this node. Of course, the question is, how do you traverse? So there's algorithms that I've built in order to do that. So what happens now is I can go and find the material. I can go then to the location code. I can traverse here down to shipper or to carrier. I can go over to tankage, then can find the asset. I can go from this over pipeline segment and go to the asset. So I have all these paths, and I can build these paths on the fly. So if I want another path from location to plant, it is very easy to connect that. And the other thing that is with the graph it does is I can add properties to the node on the fly as well. There's no schema. So if the tankage has a certain property that I want to add on at a given point in time to a certain node within that, I can do that. So a graph database allows incredible flexibility for this scenario. When we talk about cross-reference data, we're not talking about volume. We're talking more about the agility that we need in order to address or to compensate or to solve various business requirements that can come up on the fly, adding new applications and so on. So anyway, so I built this graph and did some initial tests on it, and it looked very, very promising. And then what I did, went back to all the transactions that I saw here coming over the wire, and I started doing an analysis on these transactions and said, is there a way that we can figure out a pattern or can recognize patterns, behavior patterns, when we look at cross-referencing, when we look at these transactions? And I analyzed about 250,000 transactions as they came in, so give us kind of a good population. And what is very interesting is I came across and identified 4 fundamental semantic transformation patterns that occur. And one of them is, of course, the simplest one, right? That is the one-to-one. I call it the one-to-one pattern. And that is basically, I have a key value and I find associated target value for it. Very, very simple. That is one occurrence. So we get a source material coming in and we want to find the target material or product, whatever you want to call it. Then the second one that I noticed was that we have this, what I call an enrichment, right? So I have a key value. I have a key value coming in, but I also want the target value, but I also need additional fields that the target value provides. So I want the material, product name, product code. I get the target product code, and I need also the product description or maybe the product price or whatever it is. So I have to enrich that message. The target system, it needs additional data, and that's what I call an enrichment. And then I have the third pattern, and that's what I call the dependency pattern. And in this case, I have a source value coming in, but I have to go multiple steps in order to find my target value. And that could be multiple function calls and so on. And that basically shows you kind of, when you look at a relational database, you can see, okay, I have to have this in order to find this, and then I have to have that. And there could be a condition in there, like logic operations, like an AND, an OR, and so on. So that's kind of the dependency pattern here. And then the fourth one that I identified is the granularity. And that is when I have a value coming in, like a product code, and I have multiple product codes that I have to have a selection from. And the question now is, of course, which one do I pick from the three that I have here, right? And that only can be solved if I add a condition record in some form that determines, based on some source information that I can provide, in order to figure out what is the target value that I'm actually that I need here out of this selection of these three. So these are the four fundamental patterns of my analysis, and based on these four patterns, I have now built an incredible system to do semantic transformation. And that brings me to the next big step in the evolution of this application and my research, is that I went back and I said, okay, so how do we implement these four patterns here, right? These four, and how do we connect these together so that we get a really solid system? And the way I've discovered it, the best way to do that is with microservices. So here you can see here in this schematic, you can see here there's four microservices that are running, right? So there's one, each one has only one task to do, and that is basically execute that pattern that it is in, where it has the DNA of that particular pattern ingrained. So this microservice does nothing else than an enrichment. This microservice does that only a one-to-one. This does only a granularity, and this one only a dependency. So here is my database that I showed, or my graph database that I showed you before. So what the exercise is, basically, if the enrichment gets invoked, it just does an enrichment by traversing properly through the graph in order to find the right values. If it's a one-to-one, it goes in the graph and does just a one-to-one key value lookup. If it's a granularity, it does basically based on a condition finds the value. If it's a dependency, it goes from here to there and tries to find for maybe the green node. Okay. Now the question is, next question was, I said, okay, what happens if we then take anything activity that this microservice does, this little thing here, and we record that into a database as a process log. We're logging every step that this microservice does. And what we do get with that, if we do that, we get total data lineage of what the semantic transformation actually is performing on side of this graph. And then what we do is we take that data and we funnel this through in several containers. And we basically have multiple containers available here. I show you here logregs, KNN, SVM, FNN. We're looking at GNNs right now. And we basically feed all that data into these containers in order to make predictions if we have failures coming through, if the microservice for this particular function that it is performing can't find the associated target value for it. And then I said, okay, well, there's another problem, is that we have to figure out exactly how these microservices are going to be invoked and how the middleware is going to call this. And that's why I came up with the idea of saying, okay, here's an API gateway that we're going to be calling. And this API gateway is the manager of these microservices in this universe here in this topology. Now, how do we do that? How do we know, how does the gateway know exactly which microservices should be invoked? And so I fell back on my graph idea and I said, okay, well, we can build another graph here that actually says, tells the gateway exactly how it should perform or how should it invoke these particular microservices in what sequence. And that came up to a routing graph that you see here. So here we have a route that is defined, and each microservice, you see the red ones are microservice. Again, this is directly out of my system screenshot. And you can see here that these 4 microservices are there to perform the integration of a semantic transformation of one integration. And each microservice, in this particular case, we assign a case number to it. So here's a log to tanker case ID, here's a material to material, and so on. And now what happens is the orchestrator has a roadmap to fulfill its requirement in how to invoke these microservices. So the orchestrator reads
Source.
the first node, the root node, and then actually traverses physically down these paths here. And these are the request nodes. So it knows exactly what are the request parameters it needs. And in order to find the basically target node here. So you can see it comes down here, it goes, will traverse down here, find all the request node, and then build the target node or find the target node in the graph, in the data graph. And then once that is complete, it goes to the next microservice and then does the same thing again in order to look at this one and then finds this one and so on and so on. So I built basically a recursive algorithm that actually does all of this. The beauty of this is now, okay, I can now reverse, I can change, configure this whole system any way I want in order to do any kind of transformation that I want to occur, because the router will always go based on the route here. Now, what is the advantage of this architecture? It's tremendous amount of, and wrote this down for myself just to see. First of all, this whole thing is dynamic, right? As I just said, I did this already. I moved this microservice over here, moved that one over there. I added one, we can call multiple one-to-ones, we can call multiple dependencies. We can do all sorts of things here by defining, just by defining these routes. So it's very dynamic. It is very, the process is in generic. We can identify, we can do any kind of transformation with this. Doesn't matter how we structure it, because it's all configuration based on a network graph. And then, of course, I basically found form patterns, right? So if you were to come to me today and say, okay, well, I have this particular requirement, I could add another microservice here automatically in this my topology, build a logic just for that microservice, integrate it into my route, and bingo, immediately I can address your concerns in regards to doing any kind of semantic transformation. The other thing is too, is this system is totally scalable, right? I can do vertical scaling. If I put this whole thing into a Kubernetes cluster, I can scale. So if I get a high load on this particular microservice, I can instantiate multiple microservices. So I can scale horizontal, vertically. And everything here is written to a log file. So you can see here, these are these little databases that are there. Right now I'm looking at Cosmos DB to do that actually in a JSON format. These log files are written, and then we basically consume these log files later on into our machine learning algorithms. Now, the other thing, what happens is, as these the way the orchestrator works is it passes an object between these microservices. And that's how the communication happens is, so if I pass an object here, this microservice basically populates the object, takes all the information, and passes it to the other microservice, maybe down to this one, depending on the route definition that we have. So everything is in these log files. So I can run now stats on these patterns, and I can find out exactly what the performance is. So in this use case that I've been running some testing here, you can see the 4 patterns on the top. You can see 1,964 transactions we pushed in the dependency, 3,928 in enrichment, granularity, we have 3,928, and we have 982 in the one-to-one. And then this is kind of a graph representation of what we see here on the top in these flashcards here. And then on this side here, actually, I put a little bar chart in, say, based on this case number that we have inside my routing graph, what are the errors that we are experiencing here for where we didn't find a value? And that's actually where we are really interested in. We want to solve these error problems that we are here discovering here in this process. Okay. So when we look,
Tim, the microservices are they for finding these 4 patterns?
the microservice is the pattern.
So you have 4 types of microservices then?
Correct. Yes.
Okay.
Every microservice has implanted the DNA of the pattern that it is based. So this is a microservice that just does one-to-one. This microservice does just enrichment. This one's just granularity, and this the dependency, right? So they are in the DNA of the pattern is implanted in that particular microservice in order to process. And the orchestrator is a manager of invoking these particular microservices in a given sequence that we see here, right? So I can configure this any way I want, and the router and the orchestrator will execute based what the route says, right?
Okay. And what's the logic? How does it find the respective microservices?
Based on this routing logic, which is sitting, so the orchestrator will get from the calling system, it will say, okay, here's route 100.
Yeah.
And then the orchestrator will go and find in this graph database the route 100 that is there configured, and then traverse the route that is defined in the graph database, which you see here, right? That's the route it will then take.
And what is 100 here?
It's just an identifier, so that I know which route to take, because there could be multiple routes, right?
Okay. And how does that 100 gets determined?
Oh, that's an arbitrary number that we just assign, right? That's just an identifier for which route to take. You can use an alphanumeric code. I just picked 100 for this case, right? That's just not so that the router knows which route to take here, because there could be multiple in this database, multiple routes here to define. Every interface would have its own route, right?
Okay.
So then what happens? Okay, so we see here the data that we are executing, right? And that's where we really are interested in this particular area here, because we want to kind of figure out now, how do we take this data that we have and how do we can do predictions to it, okay? So in these logs, this is an example of the log files, and this is really fascinating because you can see here, when you go back to the route, you see the red ones here. These are actually the request parameters here, these red ones here, these the yellow nodes, sorry, the yellow nodes here, they come through here, right? Those are the request parameters. So you need the request parameters, and you need, of course, some kind of response parameter. So in this case, what we're looking for, we're looking at material, with location code, tankage, pipeline segment, and what we really want with this combination here, we want to find the asset ID. And so what you do, and you can see here the live example that's been running here for this particular case, you see a request, and the asset ID. See that? And you can see here the codes that was passed down, and it found this particular asset ID here. That is the asset ID. Based on this combination, it found it. So that is exactly how it actually executed here. The orchestrator executed this particular microservice, this dependency pattern. It went down here, went into this particular graph here, took the material code, looked at the location code, found the tankage, went to the pipeline segment, and then found the asset ID that is sitting here. That's exactly how it did it here. And you can see that in this log file here, right? And you see the response code, and you see exactly what it found. So that's the reason why I put it in green. Now take the same example again. Now here's a combination of events that happened. And we can see here that, boom, there's a dependency response code. And this is blank. It didn't find anything when it went through. There's an entry missing in the node, right, in the graph, for whatever reason that made, some forgotten or whatever, okay? So what I've done now is I've taken this, as I said to you, go back to this diagram here. and that is recorded in these log. That's exactly what I showed you here, is that these log databases here that is associated to these microservices. Now we take this data here that is coming through here, and we feed that into a container that is running a logrex, logarithmic regression algorithm, or we can use a KNN, and that's the beauty of it. We can actually, I can plug in here any kind of algorithm that I want out of a set that is fittable for this in order to come up and figure out exactly and make prediction or recommendation of what this value should be that we just found that we're missing here. And that's what this graph shows here, is exactly this. And this is running on a logrex algorithm. And here's a combination on the top of the data that's coming in. You can see here, it's tankage, material code, pipeline segment, location code. These are, and this is the predictions that it makes. And it's fantastic how accurate it actually is. So for this one, it says 9.7. This is the asset code for this. This is the asset code for that. And this is the colors represent the material code. So the first test of using AI in order to do semantic transformation seemed to be very successful in our progress. Now, what we want to do in our research is we want to explore more different algorithms here, try to find out, what is the best, because what we're seeing here is that each of these microservices probably will require a different algorithm, some changes, and so on. So that is kind of the future of where we are going next with this whole exercise. The other thing too is now that I have results based here on the bottom here, these are my predictions out of this algorithm. I can now take this combination here, and it's, for me, it would be maybe a day of work to take this data here that I have and actually go back here automatically and update this graph, right? I can write a very simple program to update this graph. And so what you all of a sudden have is a complete system that is learning based on thousands and thousands of data records out of the process logs, running it through an algorithm, and then correcting itself so that when the next transaction comes in, it automatically understands what needs to be done, and so that these errors don't occur. And that is the power of this architecture for solving the semantic transformation that we are fighting with, or is a challenge in businesses, right? So where are we going for the future? Well, if you take the graph, if you take this graph here and you look at it, thousands of ideas come to mind already, right? So what I can do now is I can say, okay, well, geez, if I look at this data, these are all entities here that I see here, right? There's material, there's tankage, there's carrier, there's application, there's condition records, UML. Immediately comes to mind, I can now take this, expand this, and build basically a knowledge graph with an ontology on top of this whole thing, right? So it's very, very easy to do that now. And I can basically expand this or morph this into a complete knowledge graph for an organization to track anything inside this graph. So that's kind of the next step that we want to explore, is develop ontologies based on this graph. This would allow for another avenue of maintaining the graph by introducing new labels to it. So for example, we could take ProtoJ as a front-end tool to maintain the graph if we wanted to, and so on. The other thing that we want to take a look at is testing various AI algorithms, as I mentioned already. And the tool we are looking at is FNNs, that's the feed-forward networks, and graph neural networks, and see how they perform on this and how useful they are. Can we use them in this particular scenario? As I mentioned to you, is provide the feedback of the algorithms back in, or feed them back into the graph data, so that we basically have a self-correcting system. So there's some work that has to be done in that area, and how we best do that. And then can these concepts be used to build corporate knowledge graphs, as I mentioned to you? Can we enlarge the footprint of this graph concept and then build knowledge graphs and have other applications take advantage of that are maybe not integration related, but are more knowledge-based related, so that we can do user searches. Another area that I'm looking at it is into NLPs. Can we do, for example, do natural language processing in order to populate these graphs, extract informations as we populate the content of these graphs, and then associate maybe emails to customers, documents to customers by recognizing text information and so on. There's 101 ideas that I have in my head of what can be done with this foundation that I've built. And then, of course, we are looking for some companies that are willing to do a beta testing of this, so that we get more data, more accuracy, and understanding the environments and so on. Anyway, that is kind of in a nutshell what I have been doing, and as part of my PhD research. And I'm in the process of publishing a couple of papers on this whole concept, because I think it is very valuable. The other thing too is all of this runs in the cloud right now, and it's basically accessible from a cloud perspective. And so you could actually offer this as a service to the world, right? And build this and navigate through this, and companies could outsource their whole infrastructure, semantic transformation part to this particular service, and it provides the agility to adapt to any kind of scenario, basically. Anyway, questions? That's where I am.
Okay, excellent. A huge scope in your PhD. So coming back to that picture, Tim, go back, up, up, that graph database, up. Yeah, this one. So if you look at each of these circles, they are pretty much the entities in a traditional ER diagram with
Correct.
yeah. So how
Yes.
is so I can put the same thing as an ER diagram and put it in an RDBMS, right? How would the same concept I can put it there too?
Yes, but you have a schema that you have to follow. Here you don't have a schema.
So that means when you say I have a schema, I can put any data with any field length, type, or anything like that. Is that the advantage of graph database?
Yeah, I mean, in a relational database, these would be all tables, right? In your
Correct.
database, right? Now in a graph database, I don't have tables. I have nodes, and these
Okay.
nodes are not tied to a schema. So
the schema brings the data structure, data integrity.
correct. I
Now,
don't have that.
how is this addressed how is that problem? If I remove the schema, where is the data integrity coming into how is that taken care?
The data, a node like a tankage can have one node can have different properties to the other. That's a little bit, because you get this agility. You don't have the structure anymore as what you have in a relational database, for example, right? Where you say, okay, every record in a database has to have the same fields, right? You don't have that in a graph database, and that's the reason why a graph database is so powerful, because I can attach to one node a field which I don't attach to the other node, right? But it is a downside on one side, because you're losing the structure that you are used to in a relational database. But on the other side, you're gaining a huge advantage, because in many cases, you don't know what the properties or what the attributes are for that given node. And so a graph database allows you to do that in a graphical format. And the other thing is I can very simply move these nodes around, or attach new nodes, or come up with an extension of the topology here. And the graph algorithms that I have they're all generic recursive algorithms, right? They do nothing else than traversing, right? So that's the beauty of this whole thing, right?
Yeah, no, because what you said, you can easily move it. That kind of rationale applies to relational databases as well. But when
No, you have to.
talk about governance and everything, because that governance and the process things, when you run a company, for example, so people won't be allowing, anybody can go and easily change the data structure, right?
Correct. You would have to unload and load the data if you want to do a change, right, or something like that. Whereas in this case here, and I mean, for this particular scenario, Graph databases are becoming really, really popular, right? Because they are just so flexible, and from an analytics standpoint, they are so powerful to find data, social nearest neighbors, and I mean, page rank algorithms and all of that kind of stuff you can run over this kind of stuff, right? Which we are not doing in this case here, but we are using it completely for something different than what normally they're using it for. But I don't think there's definitely a room for relational database, and they will always be there. But for these kind of scenarios, a graph is just so much better to use because it gives the agility that you need in order to build self-maintaining systems, because you can do all of this stuff like a changing relation without basically unloading or leading or changing joins or all of that kind of stuff, right? Because by connecting the nodes any way you want, it works out to be very, very flexible. Hello?
Yeah. Okay.
Oh, okay. I thought it was gone. Any more questions?
So the graph database which you're using, is it from a particular vendor?
Yes. Right now, I started in 2019. I started using Neo4j.
Yeah.
It's actually quite interesting. And at the time, Amazon introduced Neptune as their graph database. And I actually wanted to go to Neptune. That was my intent at the time. But there was just not enough information. And so I stumbled on Neo4j. And Neo4j for prototyping this kind of stuff is really, really powerful. It is very easy to use and so on. Over the last last 4-6 weeks, I came back and I said, I looked at Neptune again, and it has some really, really neat feature. One of the issues that I find with Neo4j, it just doesn't impact me so much at the moment, is it's a property database, because it's all based on nodes and properties that you define to that node. Whereas if I go to Neptune, if I switch over to Neptune, Neptune allows me to do both. It allows me to do property databases as well as RDFs. And I'm really tending to go to RDFs on the long term, because RDFs is in a W3 standard, and it's basically the foundation for OWL, which is the language for ontologies or smart webs. And so that is an open standard. And the other thing that attracts me to Neptune is, first of all, that capability. And the second thing is that it's a service offering. So whereas here Neo4j is proprietary, I have to load it up on a server and install it there. Whereas in Neptune, it's AWS is offers as a service, which is a much better solution for this kind of thing. So yeah, I'm looking seriously at eventually moving over to Neptune. But at the moment, you know, I have so many other things that are on my plate, and moving everything over to Neptune is a significant amount of work that at the moment it doesn't create the value that I need. I need to focus on this piece here. My profits on my back to focus on that. So that's where I have to put my attention in here and come up with the FNNs. And we had a meeting last night on talking about especially the neural networks that they wanted me to try out and test out. So that will be the first part of my next step here. I call this, I build the infrastructure or minimal viable product right now that proves out the overall concept. So that's pretty stable. I mean, there's still some work that needs to be done. But then what next step is to prove out this here, figuring out which pattern has the best algorithm mapping that is along the way, and then basically feed that back, look at the feedbacks. And then the third piece would be, okay, so now let's take this off and move it into a knowledge graph. And then that particular point in time, I think it's time to reevaluate Neptune and the migration to Neptune because if we want knowledge graphs full-fledged, we have to go, there's no way that we have to go with an RDF solution.
Okay, good. Okay, good. All the best for your
Thank you.
Yeah.
Any other questions out there? Or I don't know if other people can ask questions.
I've got no questions. Just looking forward to see how this pans out. It looks great.
Thank you.
Okay, so I see Pavna is not there. She had to drop off. Okay, Tim, thank
No
you
problem.
very much for your time, and it was great talking to you. Take care, everybody. Stay safe, and talk to you soon.
Okay, look. Bye-bye.
See ya.